In this video, we discuss implementing a neural network with many hidden layers in C++. In an earlier video corresponding to this link, we discussed a multilayer perceptron. So in that video, we discussed the principles of a multilayer perceptron and its implementation in C++. But the implementation only involves one hidden layer. So here in this video, we try to generalize this to many hidden layers. This figure shows a multilayer perceptron with 3 hidden layers. The layers are indexed by L. L equals 0 is the input layer. The neurons are denoted by x0, x1 up to xn. And so there are n plus 1 neurons. And x0 is actually the bias. So that means we have n inputs. And L equals 1 is the hidden layer. It has m neurons. So L equals 2 is the second hidden layer, also has m neurons. L equals 3, the third hidden layer. And L equals 4 is the output layer. The output layer here has k neurons from y0, y1 to yk minus 1 to the k outputs. And so in our discussion, we say that the network or the multi-layer perceptron has L plus 1 layers. For example, here L is equal to 4. Okay? So from say 0, 1, 2, 3, 4. Okay, this is the L layer, the output layer. The operations of a neuron in the network is like that of a biological neuron. They both receive signals from multiple inputs. In the biological neuron, it receives electrical impulses through dendrites from other neurons. And for the MLP neuron, it receives numerical inputs from many units in the previous layer. So in this figure, it shows the input neurons. Okay. The x0 here is 1, is the bias. Okay. And we multiply 1 to W0 and then x1 to W1, x2 to W2, and so on. So we get these weighted products. Okay. And then we sum them together. Okay. And we put the sum into an activation function and get the final output. Okay. So we discussed that in a previous video. Now, this figure shows the details of the operations of a neuron. The circle here represents a neuron in a layer. The L here means the Lth layer, and J means the Jth neuron of that layer, and L minus 1 is the previous layer. Okay. So if L equals 1, then L minus 1 is 0, then this is the input layer, and A0 is X0, and x1s and so on. Okay. And this neuron is connected by the weight wij L minus 1 to the jth neuron. Okay, this is from neuron I of the L minus 1 layer. Okay. So CJL here is usually referred to as a nugget. Its value is given by this formula. It's sum over I, that means sum over all these neuron values in the previous layer, okay, the products, okay, of the neuron value and the corresponding weights, okay, with sum over I, sum over say these input neurons. Okay. So this gives us this value CJL. Okay. And then we put this CJL into an activation function, like a sigmoid function. So we get a value. Okay. And this value we call it AJL. Okay, is the value of this neuron. Okay. So at the layer L and jth neuron, and this value will fit into the neurons of the next layer. Okay. And so this is called forward propagation. Okay. So we can summarize the formulas in this way. So if L equals 0, we refer to the input layer. Okay. In this case, AI0 is equal to XI. For convenience of discussion, we also call that CI0, okay, layer 0. Okay. So it's the X values here, okay, input. And L equals capital L is the output layer, okay? And the neuron output YI is equal to AI L, capital L, okay? And this is equal to F CIL, okay, with this notation. And for other hidden layers, it means L larger than 0, L smaller than capital L, then AIL is equal to F and CIL, okay? And AIL is given by this formula, okay? CL is given by this formula. Okay. And now, with this understanding, we can discuss how to implement the forward propagation in C++. For clarity of presentation, we use fixed size arrays in our implementation. The variable names we use here are the same as the math symbols that we have used. So N1 is the number of inputs per bias. M1 is the number of hidden nodes per bias, or M plus 1. K, number of outputs. We have L plus 1 layers, or between them L sets of weights. And this array sizes L plus 1 contains the sizes of the layers. For example, sizes 0 is N1, sizes 1 is M1, and sizes L is K. And W, L, and N contains the weights. Okay, so there are totally L plus 1 layers, and L sets of weights in between. And CL plus 1 is the C we were discussing, and A, this A, okay, and Y is the output, okay, the Y here. Okay. So this is the implementation of the forward propagation. Okay. So X is the input array. So this input x, and at the input layer we set say the a0 I and c0 I to be xi. Okay, so ac will be equal to x at the input layer. Then from there we can calculate the c and h values of other layers. Because L equals 0 is the input layer, then we from there we calculate the L plus 1 or first layer. So we define the variables left to be sizes L and right to be sizes L plus 1. So that means we consider say 2 layers. So this is L and this is L plus 1. Okay, and the weight between them is WL. Okay. So we need to calculate the Z value, okay, of the output layer or the right, okay, the right side. So that's this L plus 1. Okay, and we get that from the input ALs. So here in this formula we use L minus 1 to get CJL. Okay, so if this is L plus 1, so this becomes L and L. Okay, and L plus 1, this becomes L plus 1. So basically we calculate the output load Z values, okay, using this formula, sum over all the products, okay, of the weight and D1 value of the incoming load. And then from there we calculate the A value of the output layer, okay, of the neurons of the output layer using this formula. Okay, basically this formula. Okay, but if J is equal to 0, then it is the bias, so it is set to 1. Okay, except that when we are at the output layer, when L equals L. Okay, and when this is done, then the outputs are equal to ALK. Okay, so the implementation is pretty straightforward. After we have obtained the output values from forward propagation, we can compare the values with our desired outputs or targeted outputs, and we could obtain some error values, and we use these errors to adjust the weights to the output layer. Okay, and the adjustment of the weights will cause error in the previous stage. So we again use the error to adjust the weights of the previous stage and so on. And this is called backward propagation. So the details of the backward propagation is like this. Okay. So for each output neuron yk, we calculate the error ek equals ykd, which is the desired value, minus yk. Okay. Or we also call this AKL, so it is equal to YKD minus AKL. Sometimes we can call this delta KL for the convenience of programming. Yeah. Then we calculate the gradient of the output error. So delta K L minus 1 is equal to this EK times the derivative of the activation function as CKL, okay, at the logic value. So this F dash is partial L partial CK. It is the derivative of the activation function. Okay. Then we compute the hidden layer gradient error using this formula. Okay, this is delta J L minus 1, okay, for the previous state. Okay. Sum again over the waves from J to K times the delta JK value at the right side layer, times F dash CJ. This should be CJL, okay, actually. Okay, and here L is larger than 0, smaller than L, okay, for the hidden layer gradient error. Then we use these deltas. After we got all these deltas, we update the weight using this formula. At the weight ij at the F layer, this means from the D1, the weight from D1I to J is incremented by this eta is the learning weight times delta JL times AIL. Okay. L is larger than or equal to 0, smaller than L. And now, when L is equal to 0, we are at the input layer. So AIL is AI0, it is equal to XI. Okay. And the implementation of backward propagation is also straightforward. It is like this. Now, this is the implementation of backward propagation. And YD is the desired output, X is the input. So the delta here is the delta in the formula here. Okay. And so we have L layers. And we first calculate the deltas at the L minus 1 layer. Okay, so delta L minus 1K is the E times FD. FD is the derivative of the activation function. Okay, CLK. Okay, CLK here. Okay. And then from here we calculate other deltas. Okay, using this formula. So left contains the size of the left layer, or the number of neurons at the left side layer, and right, okay, contains the number of neurons at the right side layer. Okay, so left and right. Okay, left and right. Okay, 2 layers. So we calculate the delta L minus 1 from delta L, okay, using this formula. Okay, so we find the product of W, the weight, okay, JKL times delta JKL. Okay, the same here. Okay. We find the sum, and then at the end we multiply that by FD, the derivative of the activation function, or F dash here, okay, at CLJ. And after that, we update the weights according to this formula. So you can see that this is the same as this formula. Lij incremented by eta, this eta, okay, times delta LJ times ALI. Okay, so the implementation is straightforward. This is the complete C++ implementation of the multi-layer perceptron that has many hidden layers we just discussed. This is the header file mlp2.h, and here we define the maximum number of nodes to be 30. That means the maximum number of neurons in each layer cannot be more than 30. And these are some parameters we discussed. So H is the number of hidden layers, and L, the total number of layers, is L plus 1, and L is equal to H plus 1. So these are the variables that we discussed. W is the weight, C is the longitude, A is the sum, Y is the output, and F is the activation function. FD is the derivative of the activation function, and we use sigmoid function to be our activation function. Now this is the actual code mlp.cpp. Actually it should be mlp2.cpp. Sorry. So we include this header file, and so this is the constructor with the learning rate 8 passing in, and we need to ensure that all these parameters n1, m1, k will not exceed our maximum number of nodes. And we set the sizes to be the number of neurons in each layer. And W contains the weights. Okay, we start with some random weights with positive and negative values. Okay. So the sigmoid function, derivative of sigmoid function, the forward propagation, okay, and backward propagation. Actually, sorry, this should not be here. Okay. We don't need this anymore, so I'll delete it later. And the training routine, this saves the weight, and this will read the weights back into the W array. And this is the testing routine that we used in a previous LIM video. And we use these testing routines to test our multi-layer perceptron with many layers. And here we define the maximum number of cases to be inputs to be 255. So our n1 corresponding to our n1 here to be 9. Okay, so 8 bits for input data and 1 bit is for the bias, okay. And then say 7 bits for the output, because each time we cannot remove more than half of the objects from the pile. Okay. Now let's copy these files and compile and test it. We just copied the header file mlp2.h, and let's save it. Now let's copy the CPP file also. Copy this and save it. this is the C++ multilayer perceptron. Oh, sorry. We save it, and now we can compile this. No error. Now let's copy the testing routine. So this is our testing routine, lim_mlp.cpp. So we copy this. Oh, by the way, I think earlier I missed some anchor brackets, but I corrected it. So this, we save that as mlp.cpp. Paste it. Okay. Then save it. Okay, so this is the file. And again, we can compile this. So no error now. We link this together. With MLP 2.0. Oh, sorry, it should be -o. Okay. Okay, so we created the executable lim_mlp, and we execute. So you can see that after training, out of 255, there are 5 differs in size. Okay. And now if we use only one hidden layer, then the results would be worse. Okay, so we have more errors. Now let's restore it back to three hidden layers, and well, now let's compile this first. Of course, we can always use a makefile to compile all this, but for clarity, I just do this step by step. So we restore this, and this is the lim ways. Okay, the ways that we saved. So if we modify this, we use the ways that we have saved to construct the perceptron. Then we don't need to do the training anymore. So we comment this out. Okay. And now let's compile this again. Oh, sorry, I need to link this first. Okay, link it. So we can get instant result because we don't need to do the training. We do this directly. Oh, by the way, the MLP here could be varied. So here you've we don't use C, we use Okay, it also works. We need to restore this. Compile this and link them together. Change it so it is, I guess, you sometimes slightly better results. Okay. Well, you can try this program with different cases and play with it. Okay. So this wraps up our discussion on the implementation of a multi-layer perceptron that has many hidden layers in C++. Okay. Thank you for watching, and I will see you in the next video.